It's my pleasure to introduce the session that we're calling Exciting Recent Results. The first speaker, and maybe you want to start the screen share with Tieyuan Zhu.
Yeah, I'm here.
Okay, great. We see you. So Tieyuan is an assistant professor in the Department of Geosciences at Penn State. And his talk is Lessons Learned from Implementing the FORESEE DAS Array. We're doing 9-minute talks, and Rachel will give you a 1-minute warning. Go ahead.
Herb, can you see my slides?
I can.
Okay, good. Hello, everyone. This is Tieyuan from Penn State University. So my collaborators, including my student Jim Zhu and Sam, and also the Eileen is here. And today I'm gonna show you basically two parts. One is about field experience with installing the FORESEE array here. And also I'm gonna show you some new observation from the stars array. Here I just try to ramp up a little story how we initialize this FORESEE array here. So I've been working with a university to get access to the dark fiber or telecommunication fiber. This is owned by university. So I start this conversation with the university about October 2018. Take about a few months. They can give me this access to this telecommunication dark fiber. So I give you a air view of this fiber array. You can see here's the university, and so it's about 5 kilometers long. So start from the East University and then up to the West University. And at the same time, I also start to talk with Selexa to get the box to set up. So also take a few months to set up. And finally, we gotta start our experiment from April 2019. And we use the Selexa I-2. And we're still running the experiment today. So it's a real-time monitoring for about 18 months in past 2 years. So here's the basic setup of FORESEE array. And as you can see here, this is I-2 with a screen. So you can basically parameterize the I-DARS, with all these parameters. And you see the yellow cable here. So this is internet. And with data storage, you see that black little box here. And so this is one of university buildings. So they have stable power, they have internet.
I'm not seeing your slides advance. Does anybody else?
Oh, really?
Yeah, I can't see the slide too.
Oh, sorry about that. Let me check.
Yeah, I cannot see the slide too from here.
How about now?
Okay.
Yes, now it's visible.
Yes, it's up.
Okay, sorry about that. So this is the overview of the FORESEE array. As you can see here, this is indicated by this orange line. So this is a dark fiber using the university-owned telecommunication fiber. They already been in the conduit. So I talked with the university to get access to this fiber. Here is just some timeline already set, so I don't gonna repeat that. So I really want to show this figure. Does everyone see this figure is okay? This slide? Okay, good. Thanks.
Yes.
So here I show you 3 little figures. So this is starting point. We set up this I-2 box. And at the same time, we also have a GPS, so installed outside of the building. So we have the, I believe this is the black, this is a blue line. So that's a GPS connect cable into the inside of the building. So they already have this hole for us. You know, they already have this, excuse me, hole for this cable. So we use their holes, you know, to get connected with inside of this IDARS tool. So that's the starting point. We have all this instrument over there. And at the end of the fiber, at the beginning, we do nothing about this, you know, end. We realize they have some kind of noise, backscatter energy into the fiber. That's why we, you know, we drive to the end, and then we don't have attenuator, so we kind of think a simple way, just ramp up with a pencil to, you know, reduce the backscatter from the end of fiber. And you see some parameters here. So gorge length is fixed in this IDARS tool, is 10 meters. So we select the 2-meter channel spacing. So it's 500 sampling frequency rate and about a 5 kilometer long fiber cable. Because this is a dark fiber, so we don't have a really accurate information about each sensor's location. So what we did is a tap test. As you can see here, every time I showed, you know, several tap tests, and then looking for the center of that signal. This is like active source seismic survey, right? And then we go back to the DARS data, and then we're looking for the center of the center of that signal to assign the GPS location for that sensor. We do about more than 100 locations, you know, across from the beginning of the ray to the end of the ray, and then we interpolate all this GPS location to all sensors. The total sensor is about 2,137 sensors. This is an important lesson I learned from, you know, the FORESEE arrays, the data storage. If you start a long-term monitor, so you need to consider this data storage at the beginning. For my case, at the beginning, I thought, you know, 20 terabytes probably enough for my array. So I bought the DARS, the NAS solver is about 27 terabytes. And then quickly I realized, you know, this 5 kilometer long fiber cable collected 200 gigabytes data per day, and then about 6 terabytes per month. So it's very quickly this NAS, you know, being filled full. And then I have to upgrade to a new one. So this provided me about 120 terabytes space. So far this is good enough for 2-year monitor project. And also the data transmission at the beginning. So what we connected NAS with the DARS is through the university research network. So the speed is very good, is no problem for the data transmission. But the only problem is power interruption or internet interruption. So this gonna make put the IDAS down is because once there have a power issue, so this instrument gonna be reboot. So what we have the new solution this year is a direct, excuse me, this background. So we have the new solution to connect the NAS with the IDARS directly. So we don't gonna through the internet at this time. And then we output the data using the internet. So here's the lesson I think is at the beginning, you should have a best way to get your data transmission directly, don't through the internet. If you can set up the directly transfer, that is gonna help you avoid the data gap. And last year, we also conduct this geophone active source seismic survey. As you can see here, what we did, we have 24 geophones on the surface. So we have a dark fiber in the conduit. And so this is my student, they conduct this active source with, I think more than 24, shots. Took about 4 hours field work. And we come back, we compare our geophone data with the DARS data. So we try to looking for the similarity and also the difference. So what's the difference between these two data? So the geophone here, again, this is a vertical geophone, so one component. So the DARS is more like horizontal geophone. So as you can see here, they share some similarities. For example, I label as red arrows here. And also they have some difference. You see the geophone have a very clear, I think this is ground rule surface wave. For the DARS, I didn't see very clear surface wave here. But a very interesting phenomenon is we can see the push down energy here. So this actually corresponds to the low velocity zone nearby. We also do the calibration with the earthquake teleseismic data. So here, I don't gonna go through the details here. You can follow the paper in the preprint in the solid earth. So basically, we take advantage of the L-shaped fiber, so we can calibrate two components of data with a seismometer, a three-component seismometer. You can see for two components, we actually have a very good agreement between seismometer and the DARS. For example, here the shear wave, here probably the surface wave, the surface shear wave, surface wave. So next few slides, I'm gonna show some new observations. So this is probably very common in all DARS array about the vehicle signal.
Okay, so I'm sorry, I'm so sorry to cut you off, but we're gonna have to keep it going in order to get to all the speakers. Can you wrap it up really quickly?
Yep. So I'll probably skip this vehicle signals. I think this is very interesting, you know, with the collaboration with my colleague about the airplane signal from the DARS. So as you can see, this is time frequency signal from the Doppler effect. We can understand, we can review, this is the aircraft signal. So this is how we interpret our signal with the DARS. So I'm gonna skip this. So this is a full step signal we detect. And so this is associated with the COVID-19 noise with a real-time long-term monitor from the March this year to the June. So you can see, we can see the noise decay and also the noise increase in different frequency band using the DARS. And here, if we look at the detail about the full step and traffic noise, we also can see before the pandemic, we see the strong full step noise, traffic noise, but after pandemic, we see some energy decay, and also after the green phase in Pennsylvania, we see the noise recovery.
Hi, Tieyuan, I'm sorry, but I'm going to have to cut in and ask you to conclude.
Yeah, I can, yeah, sure, yeah. Let me jump to my last slide, yeah. So sorry, yeah, this is a kind of short talk. If you want to know more, you can go to my the paper in the solid earth. So most of this material are in this paper. Yeah.
Okay, thank you.
I think we'll stop here.
Yeah, I think we'll just have to move on to the next talk. So if you would unshare your screen so that Zack can share the screen. Our next speaker will be Zack Spica. He's an assistant professor in the Earth and Environmental Sciences Department at the University of Michigan, and he will speak on ocean bottom shallow velocity structure inferred with DAS.
All right, yeah, give me 1 second. I open my presentation, my sharing desktop. Okay, can you see it fully?
Yes.
Okay, let me go back to the first slide. All right, good. Well, thank you for having me here, and also thank you to all my colleagues, especially Shinohara-san and his team in Japan, because all the work I'm going to present here actually related to an array which was developed by the University of Tokyo, the Earthquake Research Institute. And it's an ocean bottom survey with DAS. So in Japan, they have probably the largest ocean bottom observatory in the world. It's hundreds or maybe, I don't know how many, but a lot of ocean bottom seismometers, which you can see here. It's called SNet. But before SNet was created, they were like developing this cabled ocean bottom sensor. So basically you have a landing station and several ocean bottom seismometer that are connected through these cables. So that way you can record in real time and have the information of the ocean bottom seismometer directly to the landing station and then send that back to the observatory. So here what we did, we use what they did, they use one of these cable, one of the oldest cable actually that was installed by ERI, which is a cable of about 120 kilometers that sustain 3 ocean bottom seismometers, 3 components. And of course, this in order to transfer the information from the seismometer in real time, they use fiber optic cables. So we connect one DAS to one of these cable, and we sampled the 71st kilometer. So we transform this array into, well, this cable into an array of 19,000 channels spaced by 5 meters. And here in this talk, I will mainly show you the result of the first 50 kilometer of this cable, which is actually the part of the cable which is buried 60 centimeter under inside the sediment layer. So that guarantee a better coupling between the cable and the ground. Here is just an example of some earthquakes that have been recorded. So far, I think we have about 3 weeks of data. And the good thing in Japan is that, well, it's not always a good thing, but for our means, we recorded a lot of earthquakes. We have about 10 earthquakes per day in average. And so here you can see several of them and how we record P and S wave from this array. But here I don't want to discuss too much about earthquake. I want to discuss how to use information from this cable, how to use seismic wave, especially like ambient wave, to record actually I see that my camera is not on, so that you can see me as well. And so DAS underwater DAS, it records like the seismic wave that come from the bottom, but it also records like the acoustic wave that come from the top, from the ocean and from the water level. So here what you have is just a few stations, several stations. So you have the time on the x-axis and the distance, every station spaced by 5 centimeters, and you can see that there are these waves that are traveling the array. And these waves traveling at 20 meters per second, they are actually ocean gravitational waves. So literally the waves at the surface of the ocean that we can record. And if you take this type of matrix here and you transform that in the frequency wave number domain, and here look at the little red dot here, actually we are moving from the shore to the deep sea. So here we are next to the shore and we're moving to the deep sea, and what we do is a FK transform. And so here we see at the beginning, we see a clear clear amplitude of these oceanic gravitational waves. But these waves, when they enter in non-linearly in interaction, they provoke a pressure that is recorded also on the ocean of the bottom, and which is the source of the secondary microseism. And so most of the Rayleigh wave that we record on land from ambient nose cross correlation, for example, but here there's Cotley waves, so surface wave at the ocean surface, and we can see them all over the 51st kilometers of the array. So we can actually transform this wave number frequency diagram into a phase velocity frequency diagram. And here we can see that there are two clear modes of the phase velocity wave, Rayleigh waves in that case, because we have linear cable. And we can extract the maximum amplitude of this wave of this signal. And so we have something that approximates the phase velocity of these Rayleigh waves. And we can repeat that measurement all over the array. Here I did it every kilometers. So I have a 50 dispersion curves that you can invert and get a velocity model, an idea of the velocity model under the cable. So here in this velocity model, here it's like a simplification sketch of it. We see clearly like there is a Cretaceous basement, so hard rock. And on top of that, we have a softer sediment with a velocity of about 500 to 600 meters per second for the VS. So now I want just to focus on another way to get the information of this sedimentary layer using autocorrelation. So autocorrelation, it has been shown about 60 years ago that it can be autocorrelation of both ambient noise or earthquake. It can be interpreted as the reflectivity response under one station. And what you have to do in the frequency domain is just multiply your signal by itself. So, and in order like to go a bit quicker, because I only have 2 minutes left, here I will show you some results from autocorrelation with both noise and also earthquakes. So here are earthquakes. We use 6 earthquakes and we compute the autocorrelation and we stack the autocorrelation for the 6 earthquakes in order to have our autocorrelation signal. And in these earthquakes, we have both clear P and S wave. We have these V inverted shapes that are generally interpreted as a broken structure of fault structure, like complicated structure, let's say. And also we have these ghost region where actually we have no wave signal, which is probably due, which can be due to a strong topographic change, for example. And here it's the difference between the autocorrelation function between earthquake on top and the noise at the bottom here. So on the, what's interesting is that there are much more information actually from the autocorrelation from earthquake. So for example, we retrieve these inverted V shape as well. We retrieve this big, strong reflection from station 2 to 2,500 to 4,500. And then what's a bit bizarre is that the autocorrelation from noise is pretty flat after station 5,000, while there is a much more roughness in the signal of the earthquake. So if we cut a little bit the amplitude, and we can actually pick the time of this first reverberation signal, and we can do a very easy migration using the velocity we have computed before, and in order to retrieve like the depth of the interface of this signal related to the autocorrelation, which when we compare to the depth of the basement that we have with the inversion, we have pretty good agreement except in that region. So these are, so as to conclude, I just want to say that it is definitely possible to use ocean bottom cables to image the sedimentary layers and the structure under the cable. There are many techniques, ambient noise or cross correlation and of ambient noise as well, or autocorrelation is an easy to apply technique in order to have some information of the depth of your sediment layer if you have any. So now I can take question. So 9 minutes is.
Thank you for staying on time, Zach. You have just one short question. I presume you're talking about gravity waves and not gravitational waves.
Yes, yeah.
Okay. Okay, well, thank you for letting us catch up. Let me go on. Menno, maybe you want to, Zach, unshare your screen so that yes. Menno, our next speaker, can share.
Hi, thank you.
So Our next speaker is Menno Buisman. He's a PhD candidate at the Port of Rotterdam and TU Delft in the Netherlands, and he's going to talk on monitoring nautical depth with DAS and DTS in ports and waterways. Go ahead.
Thank you. I made a video presentation, so I will show that now, and then afterwards I will be happy to answer questions. I'm going to try to mute my mic, but I'm not sure if we then still have audio. So if that is not the case, please let me know.
You won't have audio if you mute yourself.
Okay, then I will leave it on. Thank you. Can everyone see it?
Yes.
Okay, thank you. Good day, ladies and gentlemen. My name is Menno Buisman, and I'm a PhD candidate at Delft University of Technology. And what I'm about to show you is probably very different from other topics. It is about using DAS and DTS for monitoring the nautical depth, which is the guaranteed depth provided by port authorities. In addition, the aim is also to change this nautical depth, which is currently based on density, and we want to change it to shear strength. This in turn should allow ships to sail through fluid mud layers as shown on the right and reduce dredging costs. So can we, by adding fibers in ports and waterways, change the way we monitor nautical depth and change the nautical depth criterion? The motivation behind changing this criterion from density to shear strength is because fluid mud is a quite complex fluid that can differ in strength like dairy products, for instance. In this example, the butter is considered to be easier to sail through than skim yogurt. Yet due to the difference in shear strength, the skim yogurt would be much better to sail through. The reason why this criterion is still predominantly based on density is because estimating density from a mud sample is way easier than estimating the shear strength. Our job is to find out if we can derive shear strength with DAS to make this change. Current methods to measure the nautical bottom are often invasive point measurements. Other methods, such as SILAS, which uses echo sounders, are limited in accuracy and are unable to derive rheological properties because it's a zero-based offset method. Another problem that occurs here is that these methods are not repeatable, which is a problem after a storm, for instance, happened, and then these measurements are no longer reliable. Plus, considering the size of these ports, once you're done measuring this whole port, then that could mean that the first measurement is already no longer valid. With DAS, it might be possible to measure at any time using noise from ships. But first, we will focus on using active sources, and we want to do something similar as done in exploration geophysics. Here, a seismic survey is used in combination with, for instance, a sonic log to find oil. We would like to do something similar on a much smaller scale using a sonic log, which would then be a coiled fiber around a tube, which we can then tie to data of a straight fiber. And we want to use the first arrivals for tomography. Another great aspect of this method is that we can combine DAS with DTS using the same fiber, making it a very powerful approach. Here you can see our setup, which we used to create a proof of concept. As mentioned before, we used a single mode communication fiber, which we wrapped around a PVC pipe. The interrogators that we have used are the IDIS system from Silixa and the DTESTA from Omnisense. This Omnisense unit measures beyond frequency and is mainly designed for measuring strain. So it's not your typical DTS interrogator. However, for us, it does serve its purpose as a DTS interrogator. Various sources proved most useful in estimating the water-mud interface and show the potential to estimate rheological properties. However, these are not the optimal sources for this purpose that I've shown here. In the field, we would rather have a broadband source and ultimately use passive noise from vessels. On the left, you can see a standard piezoelectric transducer with a 200 kHz center frequency, and on the right, you can see a dual echo sounder, which is commonly used by vessels to estimate the depth. The first thing that we tested is if we can detect these high frequency sources. And yes, as shown here, we can. With high frequencies, I mean frequencies in the range of 25 kHz to 45 kHz. This picture shows a recording time of 0.1 second, in which we sent 10 bursts. In the blue rectangle, I highlighted one of these bursts. With a stacked image, we get the first very accurate indication of the water-mud interface. Our later arrivals cease to exist in the mud, as can be seen on the right of the blue line. We can determine the water-mud interface with an accuracy of less than 1.2 centimeters, or about half an inch in depth. This is the most accurate non-intrusive method to the best of our knowledge for doing so. And all we did so far is just stack the image. Besides accurately estimating the water-mud interface, we can relate, for instance, attenuation to shear strength in a bentonite mud. Bentonite does not settle, but only builds up shear strength. The red rectangular shows our signal in the bentonite clay for the first day on the left and the second day on the right. And what you can see is on the first day we have little to no signal in our bentonite, and on the right we do get a signal, which means that the attenuation after one day has significantly changed, which is related to the shear strength buildup. Another way how we possibly can estimate the shear strength with DAS in mud is by measuring S waves. Here we applied an FK filter to focus on velocities between 800 to 1100 meters per second, which is the S wave velocity of mud. Unfortunately, the S wave velocity in PVC is 950 meters per second, which is similar to the S wave velocity of mud. This is why we see S waves on the left in the water, which is left of the blue line. Still, we can observe a change in amplitude and location of these lower velocity with time. And considering that mud settles and consolidates with time, which PVC does not, we believe that this change is related to the shear strength buildup in mud. Here you can see that on their own, TTS measurements can give a simple qualitative indication of the water-mud interface. The line with the lowest frequency is our reference line, before we start heating our column with heating rods, which were about 5 centimeters away from our fiber. As you can see, the pink line, which is the second lowest line on the left, aligns with our reference line on the right. This means that the heat from our heating rods has not yet reached our fiber due to a difference in heat conductivity between water and mud. We can also observe a somewhat linear trend in the water when we start heating on the left, and very different trend on the right in the mud. This is most likely not only related to a difference in heat conductivity, but also related to a difference in heat capacity. For this ongoing research, we are going to upscale in the Deltares lab and perform a pilot in the port of Rotterdam. The exact location has yet to be determined, but it could be in the Beer Canal, where we have these marvelous container vessels. Our results are promising, but we need to conduct more research to quantify shear strength of mud. Our focus will be on attenuation, P and S wave velocities and amplitude change with time, and we need to further upscale. This concludes my presentation, in which we showed that with using DAS, we can accurately determine the water-mud interface, the most accurate, non-invasive way to do so to the best of our knowledge. In addition to this log setup, we want to add a straight fiber to which we can tie these logs. Monitoring the nautical depth is yet another example of how we researchers and engineers with DAS at our disposal can potentially change current measuring techniques. And I am sure that there are many other purposes to which DAS can be applied that we have yet to discover. Thank you very much.
Thank you, Menno. We have time for one question. Also, I can say you can use the chat and privately message the speaker if you want to set up a later time to go over any of these talks. Okay. Thank you. Menno, please share your screen and we'll move on to Bin Lo. So our next speaker is Bin Lo. He's a postdoctoral fellow at the Colorado School of Mines, and he will give a talk titled Microseismics from Fiber Optic Distributed Acoustic Sensing the near field strain signals, and the guided waves.
Thank you, Herb. So I'm trying to share my screen here.
Yeah.
Yes.
Oh, we see you, right? So down at the
Yes.
bottom, the green.
Yes, I'm trying to share my screen right now. Thank you for having me to present. Okay, I found it. Okay. So, guess I can start. So, hello everyone. My name is Bing Luo. I'm a geophysics postdoc with the RCP consortium at Colorado School of Mines. So today I'm going to present to you some interesting findings observed by downhole fiber optic distributed acoustic sensing. There are the near field strain signals and the guided waves, as I put in the title here. And this research are the collaborative efforts with my supervisor, Dr. Ge Jing, and our RCP master student, Owen Huff, and also Dr. Ariel Lelouch from Stanford University, as well as many colleagues who have gave us their very helpful comments. So just give you a little bit of background. So in the past several years, the industry has been actively looking into the practical use of DAS in subsurface survey and monitoring. So particularly in hydraulic fracturing operations in unconventional reservoirs, there have already been some successful applications using downhole fiber optic distributed sensing to monitor the reservoir status and hydraulic fracture status. And some involve looking at the body waves emitted from the microseismic events, and say, such as the example here from Karen Beck 2019, and also some involve the VTI or even time-lapse VTI. Also, some involve the low measurement of the low frequency fracture signals when the hydraulic fracture actually touches the monitor well. So today I'm gonna focus on the microseismic part, and you will be seeing these microseismic profiles recorded by downhole DAS. And also I'll be talking about some interesting observations other than the regular body waves, PNS here. And they are the guided waves and near field signals, as I mentioned to you before. And they will require some special seismological tools to explain and analyze. So in this presentation, basically, as I have mentioned, I will cover the following two parts. The first was the microseismic guided waves. I will walk through the guided wave properties and then introduce to you two applications we have worked on. One is the seismic inversion of guided wave dispersion curves. The second is to constrain the microseismic event depth. And the second part of this talk will be microseismic near field strain signals, which will show the analytic displacement solution of a moment tensor point source, and how using this analytical solution, we can qualitatively match the field data. So let's take a look at the microseismic guided waves. The microseismic data we are using are collected from a hydraulic fracturing project at the Eagle Ford Play, and they are provided by our sponsor. And on the upper left here, this is a 3D plot showing the surface array on top, as well as the two parallel wells drilled into the Eagle Ford formation. And one is a treatment well, the other is the monitoring well. And the monitoring well has a fiber optic cable installed with the parameters listed here. The trajectories for two, along with the maximum events colored by ages. And the red curve denotes the fiber optic cable, which captures the seismic wave fields emitted from the microseismic events near the treatment well. And to the right here, this is one example of the microseismic profile. And on the profile, you can see the PNS body waves, as well as the guided waves I was talking about. So here are some schematic diagrams to give you a sense about the guided wave propagation in 3D and how it can be detected by a horizontal cable. So suppose we have a multi-layered 1D model shown on the side view here on the left. And basically low velocity layer embedded between two high velocity layers. And then the source is within this low velocity layer. And this source will emit body waves bouncing back and forth inside the low velocity layer, because the velocity contrast is trapped in the energy. And depending on the set, and this kind of body waves will basically interfere and generate these guided waves with the vertical front propagating horizontally, just like a surface wave. And depending on the sense of particle motion, we can have two types of it. One is the guided PSV, the other is the guided SH. And if we turn to a plan view for 3D case, and then the side view I've shown is just one slice from the source to the receiver in a radial direction. And so basically right now, if you have a fiber-optic cable horizontally away from the source, say a microseismic source, then you can expect to see that DAS cable is gonna detect both guided PSV and guided SH. But if we go into the details of the directional DAS response, we can see that the long offset channels, they have a cosine square theta response to the guided PSV waves. So they should the recording on the data should be dominated by the guided PSV waves. So basically, using this guided waves, we can come up with different practical applications. The first application I'm going to show you is the seismic inversion using the dispersion properties of the guided waves. And basically, for each microseismic events, we can calculate the dispersion image and make a dispersion measurement by picking the peak on the dispersion image, and then we can obtain a stable measurement by compiling dispersion measurements from multiple events. And using this measurement, we can use propagate method as the forward physics and the Monte Carlo inversion method for the inversion to obtain a best fitting 1D model, which can, as we have shown in our study, it can mesh the well log very well and kind of reproduce the same dispersion curves as we obtain from the data. So basically, we envision that this method can be for different areas where the guided waves are observable. And also we are pursuing more topics. For example, if the microseismic event distribution allows, then we can go for lateral variation of the velocity structure measurement, and also probably the time-lapse monitoring of the velocity structure. And also the 1D structure we obtain here can serve as an initial model for full waveform inversion probably. And another application I want to tell you is the guided wave, using the guided wave to constrain the depth of the events, which is mainly conducted by our master student Owen Huff. And in the microseismic data we noticed that some of the events can generate waves. So basically we assume this is because some of the events are outside of the low velocity layer and their seismic energy is not effectively trapped inside the layer. So basically, Owen has tested this idea with synthetic data and also come up with a classification method to tell if microseismic event is inside or outside the shell reservoir. So this is very important given that usually the surface array to detect microseismic location calibration is very biased and inaccurate in measuring the depth of the events. And if we can further narrow down the microseismic events inside the shell reservoir, then that could help us make a decision on well planning. So if you're interested, I encourage you to take a look at Owen's recent paper in the DAS special issue on the Leading Edge journal. So next I will switch gear to the other topic, which is the microseismic near field strain. So here's an example of the microseismic event to give you some idea about what the near field strain looks like. So to the left, I show again the map of a microseismic event distributed and the distribution and the fiber-optic cable trajectory. The beach ball here represents the focal mechanism, the location of the event. So in the middle here, the upper figure is the DAS strain rate profile. I marked out the PNS arrivals, and I just want to draw your attention to the area near the apex, and you can see this signal with reverse sign near the apex. And also I choose two vertical lines, also symmetric about the apex, and plot out the trace at the bottom here. And also I mark the PNS, and you can see there's some signal here, but not very strong. But if now we integrate the strain rate data into strain and plot out in the right column here, and you can now see the PNS arrivals are getting very strong. The signal between PNS arrivals are getting very strong, and then also and look at the two vertical lines. There you can see this very interesting increasing amplitude between P and S. That's what we are looking at. So to understand this signal, we start the analytic solution for the displacement field of a moment tensor point source in a homogeneous isotropic media. And this is actually inspired by a recent publication by Rodriguez Westerfeld on strain microseismics, where they theoretically analyzed this analytic solution in terms of strain, basically a spatial derivative of the field.
Ben?
But first, let's take a look at this.
I'm sorry.
Yes.
Can you wrap it up? We gotta keep moving on.
Yeah,
so
sure. Yeah. Yeah, sure.
Thank
No problem. Yeah. I'll wrap it up very quickly. So this is just a very complicated equation, but we are trying to use it to simulate what we see from the data. So this is just some just a synthetic example. Yes, I'll just probably skip it, but just I want to draw your attention in our time series, the traces, we can actually capture this increasing amplitude between P and S arrivals. So finally, I just want to show you the comparison between the field data and our synthetics. We can see a lot of match in the pattern, especially the sign between P and S arrivals. And also, we can also predict not just P and S arrival, but also the far field P and S. But we also have things that not matching between the synthetic and the field data. That's what we are working on trying to explain. It might be we are using a very simple assumption, so there are some more complexity in the model we should consider. So to sum up, basically I've shown you how downhole fiber optic cable with the DAS technique enables a close-up observation of the microseismic phenomena. And I have shown you two main phenomena. One is the microseismic guided waves. We have two applications. One is seismic inversion. The other is trying to use the occurrence of the guided waves to constrain the event depth. Second part is to show you some very interesting observation of the near field strain signal. And we are able to reproduce it with just a very the analytical solution of the simple model structure, the homogeneous isotropic media. And we expect to see more application of this signal in the future for monitoring of hydraulic fracturing operations. And with that, I would like to thank you for your attention. And I guess I don't have time for questions, but I would be happy to answer any. Please feel free to contact me.
So you have one question. The question is, have you tried a quantitative numerical source inversion on the data?
Actually, not yet. We are looking forward to, I mean, there are many possible directions to go into. So we are still working on it, but thank you for the suggestion, and definitely we will look into it.
Okay, thank you, Ben. Please unshare your screen for our next speaker. Our next speaker is Ethan Williams. He's a PhD candidate in geophysics at Caltech. And his talk will be on passive seismic source imaging of offshore wind turbines with ocean bottom DAS. Ethan?
Thanks, Herb. So we've already heard two really great talks today about the applications of ocean bottom distributed acoustic sensing. And there's been a bit of an explosion in the literature in the last year, and it's a very exciting time to kind of develop new frontiers of research. And in this talk, I'm kind of demonstrating and proposing that one of these may be for offshore engineering and structural health monitoring, with a particular example from, a bit of a figure glitch. That's not the right figure. Let's see if I come out of the, sorry, let me switch which presentation I'm showing. I'll go back to the PDF. Okay, that's a map of a DAS array. With a DAS array on a 42-kilometer long pre-existing ocean bottom power cable servicing a series of wind farms offshore Belgium. This was occupied in August 2018, and we have 1 hour of data. It's in relatively shallow water. It's buried under the seafloor up to 3 meters. And in particular, we're interested in looking at seismic waves for characterizing the subsurface. And we see, in a similar way that was Zack explained, there's quite a wide variety of phenomena, including ocean waves at low frequencies. But when we look, here's the same plot, but on log and linear scales. On the linear scale, we can see that above about 0.3 hertz, the recorded DAS strain record is dominated by Schulte waves and potentially other seismic modes. At the lower frequency end, we see microseism that can be quantitatively associated with the ocean waves. But at these higher frequencies, above 1 hertz, we have a number of peaks, including one here at 1.1 hertz, and a couple others here that are smaller but very sharp at 2.2 and 2.83 hertz that are presumably associated with anthropogenic sources. These are only strongly present along the outer edge of the cable between 30 and 42 kilometers in this 1 hour of data. We can see here that the frequency of these peaks varies somewhat spatially. And we can see that the higher frequency peaks are very regionally localized and very narrow. So we went originally along the same type of approach as Zack did, with the goal of characterizing the shallow shear wave velocity using a cross-correlation based approach, where we calculated cross-correlation virtual source gatherers, performed a wave field transformation, and then taking those dispersion measurements, inverted them for a sediment profile. But not all of the source locations worked quite as well. In particular, in this end of the cable where there's all of these additional high frequency Schulte wave peaks present, we observed a wide variety of other phenomena, including these really wacky hyperbolae that are really hard to interpret. And the interpretation is that these are from a secondary source of scatter. But as you can see here, the degree of interference between the direct wave and the secondary source of scatter means that we really can't tell what's going on from this sort of visualization, that measuring the dispersion in this kind of configuration doesn't work well. And so we opt for a different form of visualization, which works very well. In particular, so what I was showing before here is a common source gather, where we basically are stepping away from one of the cross-correlation pair channels. And we see this sort of interference when we have an off-axis source or scatter, because the travel time variations are very similar for the virtual source and the secondary source. Whereas here, for a common offset gather, we can basically step along the two channel pairs that are the same distance apart. And this flattens the travel time curve for the direct wave, because the distance is always the same, so long as the lateral variation of velocity is small. And it allows us to kind of zoom into what's happening with the secondary source. And if we apply this, we can see that the crazy, wacky hyperbolae that are interfering with our direct wave reduce into some very clear kind of arctangent shaped travel time curves as expected. They're strongly dispersive, so taking the envelope down here just to visualize better what's going on, we see one weak scatter or secondary source around 31 kilometers, a very strong one here in the middle, and then a large number of weaker ones that are kind of interfering with each other at the end of the cable. And presumably, given we have a cable that goes through a bunch of wind farms, these are wind turbines. But in order to demonstrate that, we want to actually take a quantitative approach. And so what we do is passive source imaging using the interferometric or cross-correlation migration developed by Schuster, which is simply a Kirchhoff migration transposed into a differential time formulation, because what you're looking at is the time difference between two channels. And we split the data into 3 different segments so we can normalize it, because some sources are weaker and stronger than others, and then compute the migration image. And we can see here plotted against the black dots, which are the individual turbines in the Northwind, Rentel, and Sea Power wind farms, that we can very clearly identify 1, potentially 2 sources in the, this one is potentially an artifact, in the Sea Power wind farm, very clearly one turbine in the Rentel wind farm, and then as many as 4 or 6 turbines in the northern edge of the Rentel wind farm. And of course, the array resolution at these low frequencies means that differentiating these more clearly is probably impossible, but we'll continue to try. So very excitingly, we also recently received some new data from this array, because part of the question is, okay, we've interpreted these as turbines, but could they potentially be construction noise? At the time that this data was recorded, the Rentel array was only partially commissioned. And also it's curious that we go through the Sea Power array, which was fully commissioned and has been for almost, for more than 10 years, but we only saw noise from one turbine. So is this like some sort of anomaly? So we were able to get 1 hour of data more recently, and this is stuff that I've done only in the last 2 weeks. I didn't know I'd be able to present this. But this is along a similar cable that's further south in a location where we saw no evidence for wind turbines, none of these high frequency Schulte waves in the 2018 data. But between 2018 and 2019, this wind farm, the Norther wind farm, began operation and was fully commissioned. And we see a complete row of turbines, which can be pretty clearly associated. There are 6 turbine sources here. This one at the upper end is the same one that was at the very bottom end of the previous image from 2018. So it's good that we see that again. And then down here, we can do the same source imaging, and it clearly needs some refinement, partially because of the disparate amplitudes leading to a patchy image. But we can clearly see that without really tweaking the parameters at all from this previous analysis, we can get a peak at 3 or 4 of these turbines correctly. And the travel time curves theoretically line up right. So conclusion here is that we can record vibrations from offshore wind turbines and ocean bottom DAS. Why is this significant though? There we go. The potential application is opening up kind of a wide variety of uses for offshore engineering and structural design and structural engineering. That in particular, we've demonstrated that you can measure the shear wave velocity, but more importantly, if you can actually measure the structure itself, the vibrations are modulated by the interaction of the structure with the soil, and therefore some of the concerns for offshore wind turbine structural health monitoring, such as the degradation of the turbines. The degradation of the turbine blades with wear and the erosion of the sediments around the base of the turbine with increasing use will change the frequency content and strength of the Schulte waves generated by the structural vibrations because of the changing nature of the structural vibrations and the changing modal frequencies. So I want to propose that this is something that we should be moving forward towards as a community, because it seems like a relatively easy application, given that offshore wind farms are one of the few places where there are a load of pre-installed fiber optic cables because of all of the power and communications and internet connectivity between them. So here's an example showing the cable map from the same area offshore Belgium. In addition, I want to point out that there's some potential engineering value of the ocean wave component as well. And I have a poster I'd like to plug, which is next Tuesday, that explores that in some detail.
Well, thank you very much. That was an interesting application in several ways. If you could unshare your screen, I think we're just going to have to move on to our final 2 talks of the session. So the next speaker is Zhongwen Zhan. He's an assistant professor of geophysics at Caltech. His talk title is Map Earthquake Hazard and Fault Zones with DAS. Zhongwen?
Thank you. Thank you, Herb. Can you all see the slides and hear me?
Yes, we do.
Great. Okay, so I'm going to talk about some applications of DAS on earthquake hazard and fault zones. So because this is a virtual meeting, I really want to get a shout out to my colleagues, especially 2 graduate students, James Adholt and Yan Yang, who did the majority of the work presented here. So earthquake hazard and fault mapping are huge topics. I want to just give a two examples as two glimpses of what I'm going to talk about. The first one is this fault earthquake damage map after the 2010 magnitude 7 Haiti earthquake. This is a pretty small area on Google Earth, and this is probably like a couple miles across the image. And you can see the damage range from almost no damage in some areas to severe damage. For example, near this hill here, this is the hill. On top of that hill is the Hotel Montana. And an earthquake engineer has attributed this to both the site amplifications and also topography related amplifications. Another example is you would imagine that in Southern California, one of the best studied region, we would know where are the faults, but that's actually not the case. This is a recent Los Angeles Times article about a multi-million-dollar lawsuit between California Geological Survey and a building development company about where are the faults in downtown Hollywood, whether they can build a high-rise building in that region. So this is, again, highlighting some of the challenges in earthquake hazard and fault mapping. So these are the two areas I want to show some exciting results. And the data I'm going to show you is from the 2019 Ridgecrest earthquake. It has a magnitude 6.4 foreshock and the magnitude 7.1, one of the bigger events in many years in Southern California. Because of that big earthquake, we got a lot of help from different people, and we were able to deploy 4 DAS arrays in the near region. So you can see the black dot showing the aftershocks of the Ridgecrest earthquake. We have 4 DAS arrays here. And most of these arrays, each one of them need really just 2 or 3 people, 1 car and half a day of time. And we deploy them, in one of these fiber hubs. So it's a very rapid way of get a emergency array to a larger earthquake. So it's going to be very useful for earthquake rapid response in the future as well. So we collected a lot of data. So the continuous data range from 1.5 months to over a year for the different arrays. So we have tens of terabytes of data. In this talk, I'm really just going to focus on this one array in the Ridgecrest City, shown as the blue line here. So this one is the closest to their, the earthquake zone. So we have about 22,000 earthquakes detected by this array that has been cataloged already by the SSN catalog. So you can see some of the example images here. So the horizontal axis is distance from China Lake Acres to the west and Ridgecrest City to the east. And this is the bigger one, 4.9, very high signal noise ratio, 4.2, 3.3, 3.1, 2.4, and 2.0. So these are all, all fairly high signal noise ratio events. So we have a lot of high quality events. Once you have so many events detected by a dense array, what you can do is try to separate the source term and the site response term using this simple equation here. Because you have many events and many channels, this is possible. It's a well-defined inverse problem. And the bottom here, I'm just showing you the result here, is the site response term as a function of distance along the cable and as a function of frequency. So the color bar here is, is already taking the log 10 scale here. So when you go from where it's red to where it's green, for example, for the same frequency, that means about a factor of 3 change in the site amplification. So this is a pretty huge change. You can see the color can change rapidly over less than a kilometer to have such a big change. You probably can relate this back to the image from the Haiti earthquake. So this is going to be very useful for earthquake hazard imaging. But we also have continuous data. So NB noise can detected by the DAS cable can be used to do NB noise tomography. Here we're just following a fairly standard approach. You do cross correlation, you get the dispersion curve, and then you do a tomography. So this is a tomography for the top 100 meters along the cable. Fairly high resolution here. And what's most exciting is that if you plot these two at the same scale, I'm just stretching them to match them. So you can see these two images have remarkable similarity, right? So you can see on the Ridgecrest end, you get much higher site amplification. And that's where you have thicker, slower sediment near the very top kind of 40, 50 meters. And to the middle, you get higher, a lower amplification. That's also where the sediment is faster. And to the very left, very west, you also get another kind of micro basin, and that's where you start to see the amplification again. So this really shows the power of using DAS to map the shallow structure, the site amplification, and use that to forecast the future earthquake shaking. So we also can use the earthquake waves to look at the fault zone faults. This was also demonstrated by Late Lindsay et al.'s science paper, but this is their one on land. This is the earthquake record. You can see the P and S wave, but you can also see some kind of chevron structures coming off the direct P wave. Sometimes you can see it on the S wave too. So these are actually body wave from the earthquake impinging on their fault zones and then getting scattered to surface wave and propagated laterally along the cable. So if we look at many of these kind of events, we have thousands of this, and if we can process them together, we can start getting a profile of, maybe you can call it, the potential for generating the scattered wave. So this is still preliminary results, but where it's blue, you don't have much scattering, where it's red, you have strong scattering. And the overlay in the background is the USGS fault database, and you can see where they think they have wear constrained fault trace, and that's exactly where we see the scatter wave, where they have inferred or kind of moderately constrained. We have detected something, but it's in a different position. We were also able to do this with ambient noise. So here in the left, I'm showing you a noise correlation profile with their channel 9000 as a virtual source, and looking at their imperial function towards all these other channels. And you can see so the left-hand half is the negative side, and the right-hand half is the positive side. But you can see the beautiful dispersive surface wave, direct wave. But you can see once in a while you have like a big scattered wave from some point, a big reflected wave. It's actually fairly strong. So you can actually map a lot of this, and also you have many virtual sources. You can use this to map this kind of reflectivity along the entire profile. On the figure to the right, we're showing some of the preliminary results, where again, red is where you are generating strong scattering. For example, the middle one seems to generate very strong scattering that's corresponding to this one over here. And interestingly, the one to the east are not generating as coherent scattering as before. So this is telling us the earthquake body wave scattering and body to surface scattering, and the ambient noise surface wave to surface scattering is actually giving us a different sensitivity to the fault structures. So this is going to be a very interesting topic in the next step to figure out what does this tell us about not only the location, but the property of these faults. So I just want to wrap up that I think DAS can be a very useful tool for mapping seismic effects and fault zones. This is a kind of urban area, but it's fairly remote. So it's a small town, Ridgecrest, and Channel Lake Acres, and its potential in like real urban areas remains to be explored, but I think it's potentially game changing. Yeah, that's all I have. Thank you.
Thank you, Zhongwen. If you could share your screen, then we can go to the final talk of this session. The last talk will be given by Siyuan Yuan. He's a PhD student at Stanford, and he will be talking about urban seismology applications of a roadside DAS array at Stanford University.
Thanks a lot, Herb, for having me. Let me share my screen. Okay. So this is actually a collaborated effort with Jingxiao Liu and Heiyang Nao in Civil Engineering Department at Stanford University. This is outline of the presentation. First, I will give you as an overview of the joint vehicle sensing and the DAS experiment. Then I will talk about what can we do with the data collected in this experiment. And so first, what is a vehicle sensing system or VS system? It collects vehicle vibrations when the vehicle passes through the target structures, for example, building, railway track, or roadway. The goal is to estimate structural health conditions from vehicle vibrations. And what is the simultaneous recording of VS and DAS? So this is a joint experiment we conducted this summer in July and August 2020. So we basically equipped our car with accelerometers. As you can see on the right, we attach the triaxial accelerometers to each wheel of our car. So we have 4 of them. And we attach the cameras in front of our car to capture the road condition, the traffic conditions. And we have a GPS receiver on top of the car to get an idea where the car is. And we perform the controlled driving along the section of the Sand Hill Road covered by our Stanford DAS array. The geometry of our DAS2 array is shown in the bottom right. And see this is Stanford University, and the black are our DAS array along the Sand Hill Road. Is around 3 kilometers long. The objectives of this experiment is first to locate fiber. You know that we have the GPS of the car, and so this can be helpful for us to locate channels and fiber. And second, we have the cars like a vertical acceleration or cars vibration known in our case because we have these sensors attached to the car, and this can be useful like to understand the sources of traffic induced surface waves recorded by our DAS array. And then for the future work, we are also interested in to assess infrastructure health condition and monitor traffic. But for this presentation, I will be focusing on the first 2 objectives. To get you a sense of what the data looks like, so on the top right, I'm showing you our the traffic recording along the Sand Hill Road by our Stanford DAS array. Vertical axis is DAS channel spacing is 8 meters. In total, we have like 3 kilometers recording, and the horizontal axis is time. We have 700 seconds. We are seeing what we are seeing here are basically cars, the quasi-static signal of cars due to cars' weight. We can see like cars traveling at different directions. So we can know car is speeding up or slowing down or even making U-turns. And so this data contains one of our driving tests indicated in yellow here. This is our car driving with constant speed along the road. And at the bottom is our car making U-turns on the Sand Hill Road. Our DAS system also capture it. And secondly, I will want to show you an estimate of conduit location work we're working on from like inverting from quasi-static recordings. So begin with, I want to show you we can locate the channels along the fiber, like using quasi-static signals of cars. Here I'm showing you a quasi-static signal like from 0.2 to 30 hertz. Actually, the quasi-static signal is below 0.8 hertz. It's pretty low frequency due to cars' weight. And from the quasi-static amplitude, we can estimate cars' arrival time at each channel, right? And we also have like a car's GPS recording. And together with these 2 types of information, we can estimate the channel locations along the fiber. So this is the data produced by our car driving with constant speed, indicating yellow here. We use this data, we can map the channel to on the DAS fiber. And the result is shown on the left. We have the channel numbers labeled here based on the estimated location of each channel. And to validate if this is accurate or not, we use this data on the top right here. So this is a U-turn data. And what we did is that on the bottom is that we utilize the estimated channel location and the GPS recording. We just overlay the GPS recording here, and we see the GPS recording matches the quasi-static signal, which indicates our channel estimation is relatively accurate. We are not only interested in the channel location along the fiber, we're also interested in how deep the fiber is buried underground. And this information can actually be recovered from quasi-static waveform. I'm showing you here on the right are our car, like driving with the same speed, but as different car lanes. You see that the first lane is closest to the DAS fiber, so the amplitude is the strongest. And from 2 to 4, the car lane is further away from DAS channel, so we are seeing like amplitude drop. And what I'm showing on the left is a stack of 5 channels in the center, like within these 2 yellow dash line. Like let's say for lane 1, I shifted the 5 channels in the center, and then I do a stack, and I got the blue curves on the left. And I did the same thing for the other three lane. I got the other three curves. We see in the amplitude drops. And so the goal here is that we have this one, the polystatic waveform. We want to estimate fiber depths and Poisson ratios. This can be viewed as an inversion problem. The forward modeling steps can be using like a Boyce-Netsky theory, which assumes elastic and isotropic half space. And we can use grid searches over fiber depths and Poisson ratios to find the best fit to these observations. Let me show you the results. On the left is the observation of the quasi-static waveforms we have. And in the middle is the best fit we got using grid searches over cable depths and the Poisson ratio and the Boyce-Netsky theory. And the normalized cross correlation between the ground truth and our simulation is 0.975, so it's pretty high. And the estimated fiber depth is 0.4 meters, and estimated Poisson ratio is 0.42 42. So this will be, the fiber depth estimation will be validated in the future. So we are going to use a ground penetrating radar to validate these results. And the third thing I want to show you today is the source characterization of the traffic-induced surface waves. So first I want to show you, we observe amplitude correlation between our DAS array and the vehicle-based accelerometer signal. And on the left, I'm showing you U-turning data. This is generated by our equipped cars. So, and on the bottom is a car speed from the speed sensor installed in the car. And what we did on the top right is that we following the car trajectory, and we just plot the amplitude following the car trajectory of a DAS array, and we plot it on the top right. On the top right, notice that this is not raw data, it's the curvature of DAS. It is basically a second derivative in time of the raw strain recordings. We are looking at a dynamic response, not quasi-static. And below are the car's accelerations recordings recorded by accelerometer installed at the 4 wheels. So we have 4 of them. And we are seeing that these two types of recording has some like signature in common. For example, we see amplitude jumps in all of the sensors. You can see that there is amplitude jumps. So these jumps can be related to bad road condition. Also, we also observe the spectrum consistency between these two types of recordings. On the top left, I'm showing you our car hitting a metal plate, exciting strong surface wave. And we also see from the car's acceleration signal here, we also see amplitude jumps there. In the middle, I'm showing you a dispersion spectrum image of the data, of the DAS data surrounded by these red rectangles. So we see pretty good signal to noise ratio because our car hitting the metal plate on the road. And on the right, I'm showing you the power spectrum density comparison between our DAS shown in black and the color power spectrum density for the car's acceleration at 4 wheels. And we are seeing a pretty consistent, frequency peaks circled by these red circles. And what about normal road condition? I'm plotted here down in the below. So if we look at the bottom left, it is for the normal road condition at the channel number 480. We see less signal to noise ratio for both DAS recording and the car's accelerations. And for the dispersion spectrum, we see less signal to noise ratio as well. But if we look at the power spectrum density, still we see it's kind of like we see kind of consistent frequency peaks for both our DAS and the car's acceleration. So this implies that it's likely that the DAS surface wave recording spectrum is related to car's vibration mode. What about other track? Our DAS array also record a track passing the same channel as our car, the channel 480. This is normal road condition. For track, we see a strong surface wave with much higher signal noise ratio compared to our cars. And we can see also this from the dispersion spectrum. And also, we look at the power spectrum density. It has different spectrum patterns compared to our cars. So
Hey,
it indicates
Siyuan?
different. Yes.
Would you mind wrapping it up quickly?
Oh, sure, of course, yeah. Let me do that. So we see that different car can have different vibration mode and different DAS response. And if we have like include a longer offset for track, we can even recover lower component frequency as low as to 2 Hz. But with our cars, we have less signal to noise ratio. So to wrap up, we show an overview of the VS DAS experiments, and we performed the fiber location estimation using quasi-static recordings, and we performed and we studied surface wave recorded by DAS can be related to cars vibrations. And that's all I want to show. And thanks a lot.
Thank you very much, Siyuan. That was quite an interesting application of DAS. So I want to thank all of our speakers, and we're into the break. I'm going to turn it back to Scott, who will officially put us on break.
Okay, we are officially on break, ladies and gentlemen. We will return at 1/2 past the hour, so that's about 20 minutes from now.